Okay, good morning, everyone. How did the homework go? Please put your question on chat so we can get started. We have 1 minute to go yet still. Okay, any questions from the homework? Danielle, can you go over 21? Definitely so. Any other questions beside that? Okay. So let us recall the main definitions and then we proceed. So the main definitions were, first, a vector V is, so we have a n by n matrix. That's really, of course, my starting point. So V eigenvectors, if A, V, so when you let A acts on V, it just scales the vector V by a scalar. That's what an eigenvector. Lambda is an eigenvalue if we can find a non-zero vector x such that ax equal lambda x. This means if ax equal lambda x has a non-zero solution. That was our. So if ax equal lambda x has a non-zero solution, which was equivalent to say that ax minus lambda I times x equal to 0 has a non-zero solution, which means the determinant of a minus lambda I has to be equal to 0. Okay, so basically those were the definition. And then we talked about the algorithm, which was to find eigenvalues. To find the eigenvalues, we set the determinant equal to 0 and solve for lambda. And to find the eigenvectors, we solve the system. We solve the system A minus lambda I x equal to 0. And to find what we call the basis for the eigenspace, once we solve the system, we write the vectors in parametric vector form and we extract the basis for the eigenspace. So this is a little bit of a quick summary of our definition. Now I go to your classmates' questions and I will work out one more example to elaborate one more time how to solve the eigenvalues, eigenvector problem. So number 21, I read it and I would like you guys to answer the question. So part A is, there's a true or false question. A tells us the following. If ax equal lambda x for some vector x, then lambda is an eigenvalue of A. So the question is, so that's section 5.1, part A. I hope you guys have the book in front of you so you interact with the question. The question is the following. If ax equal lambda x, if this holds for some vector x, then lambda is an eigenvalue. And the question is true or false? Back to you now. So suppose this is the case. The question is this a true statement or a false statement? True, you justify. False, you tell me why it is false. Back to you. Anybody have any input? True or false? Okay, Matt, tell me true. True, everybody tells me true. Okay, so there is an agreement that the answer is true. And my answer would be not true. Yes, exactly. There is a problem with the solution. Yeah, it's true if there is non-trivial solution. Now it's absolutely correct. But here they do not tell me for some non-zero x. They tell me if ax equal lambda x and lambda is an eigenvalue, true or false. This is a false statement. The correct statement should be if ax equal lambda x has a non-zero solution, then the answer would be true. Since they did not tell me that x is non-zero, the statement will be false. Because if I take a times 0, this will be always equal to 0. Doesn't mean that the lambda will be an eigenvalue. So this statement is false because they did not specify that this x has to be non-zero. That's why it is false. If they had said x non-zero, then the statement would have been true. By not specifying x, the statement is false. Now, part A, question B. B is the following. A matrix A is not invertible. So I just write it down because it's important. A, not invertible. A is not invertible if and only if. So if and only if 0 is an eigenvalue. Is the statement true or false? You may need a little bit of thinking about that. So they are relating to ideas. So A is not invertible if and only if 0 is an eigenvalue. True or false? You need to think a little bit about it. I'll let you do that. Okay. So what can relate to invertibility and the fact 0 is an eigenvalue? Okay, Angela says true. And of course, the answer true will not be accepted unless it's justified. So why it is true? So why, if A is not invertible, 0 will be an eigenvalue. So Trent, what does it mean for 0 to be an eigenvalue? What does this mean? Try to basically think about that. Okay, think about it while you write it on another sheet of paper. Somebody tell me it's true, and we need to interact with that. Any input? Try to make sense out of this. What does it mean for 0 to be an eigenvalue? This would help us a little bit. So 0 is an eigenvalue means what? Let's go back to the definition of the eigenvalue. Lambda is an eigenvalue. It means AX equal lambda X has a non-zero solution. Now my lambda here is 0. So A, 0 is an eigenvalue. This means that AX equal 0, that's the lambda, times X has a non-zero solution. Okay, which means the following. It means that AX equal to 0 has a non-zero solution. So if AX equal to 0 has a non-zero solution, what does this tell you about the matrix A? That tells me exactly that the matrix A is not invertible. Okay, so that's why the statement is true. So 0 is an eigenvalue. Following the definition, it means you can find a non-zero vector x such that AX equals 0 times x has a non-zero vector. So it means that AX equal to 0 has a non-zero solution, and that's exactly what the non-invertible is about. Okay, so that's why the statement is true. Okay, now we move to C. A number C is an eigenvalue if and only if the equation, so C eigenvalue, so instead of calling it lambdas, I call it C. C eigenvalue if and only if the following, x equal to 0, has a non-trivial solution. True or false? Quickly, that's an easy question. The only hard question was B. That's absolutely true because that's the definition. That's not really the definition, but that's what how we derived it. If lambda is an eigenvalue, it means AX equal lambda X has a non-zero solution. And when we rewrote this equation, we wrote it exactly in the format A minus lambda X times equal to 0 has a non-trivial solution. So we basically rewrote it in the exact same format. So this statement is absolutely a true statement. And finally, D tells me the following. I will not write it, but I want your answer, but I will read it very carefully, very slowly actually. It tells me that finding an eigenvector for A may be difficult, but checking whether a given vector is in fact an eigenvector is easy. Is it true or false? Back to you. So finding the eigenvector is maybe hard, but checking whether a vector is an eigenvector is rather easy. True or false? Absolutely true, because checking whether a vector is an eigenvector, you just take A times the vector. If it scales it, that's an eigenvector. So that's really not hard. To find the eigenvectors is a long process. We have to find the eigenvalues first, and then we proceed to find the eigenvectors. There is no way out. E is important. To find the eigenvalues of A, reduce A to echelon form. True or false? Means if you have A, just reduce it, and then we can find the eigenvalues. True or false? Absolutely false, absolutely false, absolutely false. Because finding the eigenvalue is not, we are not working with A. Finding the eigenvalue, we're working with A minus lambda I. We're not working with A. We're working with a new matrix, which is A minus lambda I. So A is not finding the echelon form of A is not, because that's the matrix we'll be actually working with. Okay, so that's actually this is a nice problem because it brings up ideas. Before we move on to the new sections, I would like to, whether you ask questions or not, I would like to work one problem myself. with eigenvalues and eigenvectors. Unless you have specific questions, I will address. Otherwise, I will take a problem myself and work it out. So, do you guys have any questions from the homework? Please do the homework. We still have 1 week to go, and it will do you a lot of good. So I will take the first following problem, which is in my note, and I will work it out fully. So I have the following matrix A, which is -1, 1, 1, and 4 to 4, and 0, 0, -2. Okay, and the question is, basically, I want to find the eigenvalues for this matrix and basis for the eigenspace. So this is my matrix A. So first find the eigenvalues. Okay, so how do we find the eigenvalues? We have to take the determinant of A minus lambda I, set this equal to 0, and solve for lambda. So first, we have to take the determinant of A minus lambda I. Now, how we compute A minus lambda I? Basically, we take lambda away from the term along the diagonal because we're taking them from the identity, and everything else remain the same. So this will give me -1 minus lambda. That's give me a 1. That's give me a 1. That's a 4. And that's a 2 minus lambda, and that's a 4. And finally, that's a 0. That's a 0. That's a -2 minus lambda. And now I need to compute this determinant. How do you want me to compute the determinant of this matrix?
Cofactor expansion across the third row?
Immediately. Immediately. That's the only way out. Usually, finding the eigenvalues for a 3 by 3 matrix is actually not trivial. Because when we find the determinant, what we're going to end up having is basically a cubic equation. It means equation that involve lambda to the power 3. You will see that in a minute. And solving a cubic equation is not easy, as by now you guys should be aware of. So finding the eigenvalues for a 3 by 3 or 4 by 4 become really not an easy problem. And that's why a lot of, as usual, MATLAB and other computer algebra system, they actually can solve them by not by kind of complicated techniques. However, in our class, because we want to learn how to do them, usually they are doable. So I usually give you a matrix where you can compute them with certain ease. So immediately here, I have to do cofactor across this row. So which will give me -2 minus lambda times, so this is my cofactor, and that's plus, minus, plus, minus, plus. So that's the checkerboard sign, times the determinant of the matrix, -1 minus lambda, 4, 1, 2 minus lambda. And remember, finding the determinant is solving. So this will give me, I will factor out this minus because it's, and then I will multiply here, -4. Okay. And I need to solve this. Remember, that's what I want to solve. So it's equal to quantity -2 plus lambda times. Now I need to basically distribute. So this will give me a lambda squared from here, minus lambda -2 lambda. And then I will have -2 -4 -6 equal to 0. Again, solving is factoring. So once an expression is already factored like this, we don't distribute because I already see one eigenvalues, lambda equal -2. So this is going to be equal to -1, 2 plus lambda, times I need to factor this term, memory, I did something so that we can do that. Right? So what are the factors here? 2 and 3, obviously, lambda and lambda, and I should have a minus. They have something wrong. Minus minus plus lambda minus 2 lambda. So it's going to give me minus lambda. Sorry. Okay, so by doing this, I will have minus 3 in here, and I will have plus 2. So this will give me 2 plus lambda square with a minus in here, lambda minus 3. This is equal to 0. This will give me 2 eigenvalues, lambda equal minus 2 and lambda equal to 3. Okay, so that's how we find the eigenvalues. Now the eigenvectors for this particular one, and usually the question is find a basis more than anything else. So we will find a basis for that for each one of them. So I'm going to take a basis for, I will do only one of them because you should be able to do the rest. Basis for lambda equal minus 2. It means basis for the eigenspace. So for that, I need to solve. I need to solve the following system. A minus lambda x equal to 0. So be very careful, the lambda is negative in this case. So to make things easy, it means I need to solve this system. So now I go back to my A, right there, and I plug in because I have to see my A. So the system I need to solve, A plus 2r, minus 1 plus 2, which is going to give me a 1, 1, and 1. And then 4 plus 2, which gives me a 6, a 2, and a 4. Then it's a 0, it's a 0. And minus 2 plus 2 is 0. Now, we should get a non-zero solution. If we don't, it means, as I said, either the lambda is wrong or the algebra is wrong. Means when you reach this stage, we have to have a non-zero solution.
For the finally, shouldn't it be 444 instead of 624?
I usually do stupid mistake, and I trust you guys. Okay, so this will give me 1, 1, 1, 0. Minus 4 plus 4 is a 0. Minus 4 plus 2, it's a minus 2. Minus 4 plus 2, it is a 0. And 0, 0, 0. Okay, so leading. I solve right now. So when I solve, I will get x3 free. x2 is 0. And x1, x2 is 0. So this first line, this first row read x1 plus x2 plus x3 equal to 0. x2 is 0, x3 free equal minus x3. And the solution, the 2 in the middle, should be a 4. The 2 in the middle should be a 4. Any other mistakes? And okay. So the problem is more interesting. Thank you very much. And I remember I wrote the problem to have that. Okay. My apology, 1, 1, 1, and then I'll give me 0, 0, 0. Very good. So this is what I want actually. So this will give me x3 free, x2 free. I have 2 free value. And x1 is minus x2 minus x3. Okay. Now I need to write this in parametric vector form. So in parametric vector form, I will set this to be in S. I will set this to be my T, this will become minus s and minus t. So in parametric form, my vector will have the following format. S times minus 1, 1, 0, plus t times minus 1, 0, 1. It means every eigenvectors that correspond to lambda equal minus 2 means every vector that has the property ax equal minus 2x, every one of them is a linear combination of those following two vectors. So there are a lot of vectors that satisfy this, and each one of them is actually a linear combination of those two. So basically, geometrically, if I have the two vectors, minus 1, 1, 0, and the picture is absolutely upscale, but if I have those two vectors, that's my 0, and I look at the plane, that's the span, I look at the plane. Any vector in here, if I take any vector within the plane, any vector here, and I compute a times x, so I take any vector here, I take my original matrix, multiply it by x, the a times x is going to be somewhere here. So within this plane, a acts very nicely. It's just stretch the vector. So as long as I am within the plane determined by those two vectors, any x within this give me ax equal minus 2x. It's very restricted. So now the basis for what we call e minus 2 in this problem will consist of two vectors, because we need two vectors, linearly independent vectors, to give me every possible eigenvectors that correspond to minus 2. So the basis here is minus 1, 1, 0, and minus 1, 0. Okay, and the dimension in this case, the dimension, I remind you, is how many vectors are in the basis. So the dimension in this is actually equal to 2, because that's how many bases form. So the eigenvectors in this particular problem that correspond to minus 2 are actually a plane in R2, in R3. They are a plane in R3, which is just the picture. Every vector in this plane, when you compute a times this vector, is very easy picture. It's just stretched by a factor of minus 2. And the dimension of that, which is how many vector in here, is equal to 2. Now for the other eigenvector, for the other eigenvalue, it means for lambda equal whichever we got, minus 3, the problem is simple. You just solve, and in that case, you will find only one vector in the basis. Please, any questions before we move on? And if I do any mistake, make sure you point them out on chat. Now I need some terminology before we move on to the following section that we should be aware of. So I will read this terminology and then I will explain everything verbatim. So this is the terminology that you should know. 1 minute, please. Okay. So I'll put them out and then I'll explain it in an example. So let A be a n by n matrix. Before I explain the idea, let me go back to the problem I did a minute ago, which is for the 3 by 3 matrix. When I computed the determinant of A minus lambda r for the 3 by 3 matrix, what I got is actually a polynomial of degree 3. So when we computed this determinant, right there, A minus lambda I, what I got is a polynomial, and the degree of the polynomial is 3. In other words, if you multiply out the lambdas, you get lambda to the power 3. So the determinant is a polynomial. Polynomial means it's a function where the only that of the form x cubed plus x squared plus x, or x4 plus 5x squared. It means the only power of x that shows up are the integer power, positive integer power. So if I have a 3 by 3 matrix, usually the determinant is going to be a polynomial and the degree is going to be equal to 3, the size of the matrix. If I have a 4 by 4 matrix, the codeterminant is going to be a polynomial of degree 4. Now, those polynomials are given a name, and they are called characteristic polynomial. So this is terminology. Let A be n by n matrix. Then the determinant of A minus lambda I by itself, we give it a name, and we call it the characteristic polynomial of A. And it's a polynomial of degree n. 3 by 3, polynomial of degree 3. 4 by 4, polynomial of degree 4. So that's what we call the characteristic, and I spelled characteristic wrong, characteristic polynomial of A. When we solve the equation, determinant of A minus lambda I equal to 0, so this equation that we need to solve to find the eigenvalue, people call it the characteristic equation of A. So those have names that we should be familiar with. So this equation that we solve to find the eigenvalue, we give it a name, we call it the characteristic equation of A. 3, another terminology. Suppose we solve this equation and we find an eigenvalue. Let me call it lambda 0. So lambda 0 is an eigenvalue. That is a solution of determinant equals 0. Then the algebraic multiplicity of lambda 0, the algebraic multiplicity, is the number of times the factor lambda minus lambda 0 occur when the determinant is completely factored over the real and complex numbers. So the algebraic multiplicity of the determinant, it means when we factor out the determinant, how many times the factor lambda minus lambda 0 occur when we completely factor. So in the previous example, right there, when I compute the determinant and I completely factor it, I mean, there is no room to factor anymore, I got lambda plus 2 to the power 2 and lambda minus 3. We're going to say that lambda equal minus 2 is of algebraic multiplicity 2, because that's how many times the number of the factor 2 plus lambda occurs when we factor out the totally the determinant. Lambda equal 3 will be called of algebraic multiplicity 1. The last definition is the following. There is something called the geometric multiplicity. So again, if lambda 0 is an eigenvalue, the geometric multiplicity is the dimension of the eigenspace. So whatever lambda 0, once we compute the dimension, that's called the geometric multiplicity. So it's a little bit of terminology that we should be aware of when we talk about eigenvectors and eigenvalues. So I'm going to give now one example to basically kind of review those terminology. And this is the example. I'm going to take a matrix, and for that I will take a 4 by 4 matrix just to make it a little bit not harder, but just to elaborate all those definitions. So I'm going to take a 4 by 4 matrix, and it's all in your notes. So 4 by 4, 1, 0, 0, 0. I took an easy one for a reason. Minus 1, 2, 0, 0. And 4, 1, 2, 0, and finally 1, 2, 3, 2. This is my matrix A. And my first question is find the characteristic polynomial. So the characteristic polynomial, it means I need to find the determinant of A minus lambda. All right, so what's the determinant of A minus lambda I? All right, so we do it. 1 minus lambda, minus 1, 4, 1, 0, 2 minus lambda, 1, 2, 0, 0, 2 minus lambda, 3, 0, 0, 0, 2 minus lambda. So quickly, what's the determinant of this matrix?
The product of the terms on the diagonal.
Exactly, it's product. Because we talked about that in class, that if you have a triangular matrix, triangular, it has to be, then it is the product. So let us multiply this. So 1 minus lambda times 2 minus lambda to the power 3. So I gave this type of example to point out this idea. Now, what's the determinant? So that's what we call the characteristic polynomial. That's a polynomial. Degree is 4. We have a 4 by 4 matrix. We have lambda 3 here and lambda, that's lambda to the power 4. That's why solving the eigenvalue eigenvector problem is hard, because if I want to find the eigenvalue for a 4 by 4 matrix, I will need to solve a polynomial of degree 4, which is very, very hard. And that's why they had MATLAB, the one that you guys work with the most, has a lot of algorithm to be able to deal with those type of problems. Question number 2 is find the eigenvalues. Eigenvalues and what their multiplicity. So find eigenvalues and state their algebraic multiplicity. Okay. So find the eigenvalues, it means we need to solve that. Of course, I gave a simple scenario equal to 0. Means one solution is given by lambda equal 1, another lambda equal 2. This one, the algebraic multiplicity is 1, but I cannot factor anymore. That's how much. This one, the algebraic multiplicity is 3. So that's what we mean by algebraic multiplicity. Now the last question is, I want you to find basically this one, the geometric multiplicity of lambda equal to 2. Basically, I want you to find a basis for the eigenspace that correspond to lambda equal to 2. To do that, we basically need to solve this system. X equal to 0. It means in my mind, I'm trying to find all the vector x that when A acts on them, it just stretch them by a factor of 2. That's really in the back of the mind. Which vector A only stretch? Doesn't really do much to them, doesn't change them, just stretch them. Very good, so we have to solve this. So I will definitely start a new paper here. So I need to compute A minus 2I and a 0. So this is my A, right? Just staring at me, and I need to find it. So let's do that. 1 minus 2 minus 1 minus 1 4 1 0 2 minus 2 0 1 2 0 0 2 minus 2 0 3 0 0 0 0, sorry, and I'm solving a system. I should never forget that. 0 0 0. Now I have a leading here and a leading here, but I have a 3 in here. I cannot proceed till my matrix is in echelon form. Definitely the 3 does not belong, so I have to perform the whole picture now. 1 2 3 4 0. I have to get rid of 3, so I multiply this one by divide by 3, multiply this by minus 3/2. So will give me minus 3 plus 3 0. So I perform my operation to get me a 0 in here, and I will have 1 2 0 minus 1 minus 1 4 and 1. So I keep track with my leading. My matrix is in echelon form. I can start solving, or I can do one more step and make it in reduced echelon form. So I will go one more step, make it into a reduced echelon form, and turn those plus minus into a plus. So I get that 0 0 1 2 0. So I will have to multiply by minus 4 and add it. Minus 4 plus 4 is a 0. And here I will have minus 8 plus 1, which is going to give me a minus. Am I doing any mistake? Any mistake? I think so. Where, Matt? Where am I doing a mistake? With the 3, the matrix is in echelon form. No. Oh, here. Yeah, you're right. Why I'm doing this? I don't know. I have no idea why I'm doing this. And I think I did it in my notes as well. My apology to you. So this is 3 stays here and is 0. Well, that's more interesting than I thought. Okay. So finally, yes, thanks, Matt. Please stay with me. I have to correct my notes as well. 1, 0, 0, 0, 1, 2, 0. So basically when I sum, this is going to become a 0 here. And minus 1, 4, 1. So minus 1 plus 1, I will make this into a 0. And minus 4 plus 4, I will make this into a 0. So, and this I will make it into 1. So I will have 1, 1, 1. So this would give me the following. That x will be equal, so I have one free variable t. And this, I get 0 for that. I get 0 for that. I get 1, and I get minus 1. So the basis, granting I didn't do a lot of mistakes, which is I have a hunch I did, 1, 0, 0. That's the basis for E2. So it means that the dimension of E2 is equal to 1. So here is the thing. The geometric multiplicity is 1. Algebraic multiplicity is equal to 3. So these are the terminologies that we're using. Okay. All right. Now we're going to start a little bit some application. Our first application of the eigenvalue eigenvector problem. What's interesting about them is that I know this seems very bizarre to you, but they come up almost a lot. I mean, they come out of nowhere. You will be solving a problem, and out of nowhere, they come up. They come up in the following scenario. All of a sudden, you realize that your matrix stretch a vector. And the question is, how can I find them? So that's really they come up by you're working with a matrix, you're working with vector, and then you realize that what A does to those vectors is to stretch them. And then you start asking yourself, okay, how can I find those lambdas? So that's really how they come up. They really come up almost out of nowhere, but they always come up. So our first application for that is the idea of what we're gonna call diagonalization. So I will start it today, and we work with it a little bit more next time. Diagonalization. Okay, what is this? Again, suppose I have a matrix that's a n by n matrix, a n by n matrix. What does it mean to say a diagonalizable? A diagonalizable means that you can actually write it as a product of simple matrices. So let me read the definition. A matrix A is diagonalizable if I can write A like that. A matrix P, a diagonal matrix D, D is diagonal, and remember, diagonal are the matrices which have term along the diagonal and zeros everywhere else. That's a times the inverse of what we start with. So A is diagonalizable if A could be written as a certain matrix P times a diagonal matrix times the inverse of the first matrix. We can factor it out in this way. So before we start learning how to do it, one simple application to, okay, if a matrix could be written like this, the idea is that it will be a little bit too easy to work with it algebraically in the following sense. Suppose a matrix is diagonalizable. Is a diagonal matrix. Let us say 2, 0, 0, 4. And what are the eigenvalues of this matrix? Can anybody tell me? Quickly. What are the eigenvalues of the matrix D? Can we spot them?
Would it be 2 and 4?
Exactly, 2 and 4. But that's a diagonal matrix, because when you compute the determinant, what will happen? It's 2 minus lambda, 0, 0, 4 minus lambda. So determinant is going to be the product equal to 0. Lambda is 2, lambda is 4. So if you have a diagonal matrix, you know, those are very easy matrices. These are really the easiest matrix really to work with. First, you can immediately just spot their eigenvalues. They're going to be 2 and 4. Another simple thing to do with diagonal matrix, you can actually take their product very easily. Remember, multiplying matrices is not trivial. But if it's a diagonal, it's very easy. Suppose I multiply the matrix by itself. D squared, it's mean D times D. So how do you multiply it? Let us do one problem and then the picture become easy. 2, 0, 0, 4, 2, 0, 0, 4. Only diagonal, we have this simple fact. Let's multiply them. 2 times 2 plus 0 square, I know it's 4. 0 plus 0, 2, 0, 4 square. Okay, let's come up with, take it to the power 3. What do we get? I think, so it is D times D times D, or it's D squared times D. And that's D squared times D. Okay, we multiply them. We get 2 to the power 3, 0, 0, 4 to the power 3. So what is the pattern? If I want to multiply D to the power 10, is it easy or hard? What's D to the power 10? What's the pattern is telling me? You guys can do it. You take the term along the diagonal, you raise them to the power 10. 0, 0, 4 to the power 10. So if a matrix is diagonal, taking its powers is actually simple. We just take the power of the term which are on the diagonal and the rest is 0. So if you have an easy diagonal matrix, it's very easy to work with. First, its eigenvalues are immediately the 2 and 4, but then also you can take its power very, very easily. So they are simple matrices to work with. Now, if a matrix is diagonalizable, finding its power will be also very simple. So suppose I have a matrix A, and this matrix I can write it as, suppose I have a matrix A, and I can write it as a P times a D times a P inverse. And we're going to learn how to do that. That's the goal of this section. So supposedly I have the following matrix A. So suppose this could be written, this is my A, and by certain magic, I can write it like this. A certain matrix P, let us say that's 1, 2, 3, 7. That's the one from the notes. And 2, 0, 0, 4, that's my D. And this is the inverse of P. Okay, the inverse of P, it means we know how to compute the inverse of 2 by 2 matrix. The determinant is 7 minus 6, that's a 1. So I don't have to worry about that. Then this is 7 and 1, minus 3 and minus 2. So suppose A could be written like that. And I want to compute its power. What's A squared? Now you can compute this, you get something. I don't really want to worry about that, but I want to compute A squared. All right, I can sit down, multiply those out, you get something, and square it. But we don't want to do that. We want to make use of the fact that it is we can factor it. So it's going to be equal to this times that, because I can factor it out. But this will give me what? Where the simplicity is going to come. Those two combined will give me the identity. Am I right? So this will give me a P times D, that's the identity matrix. That's P inverse times P, times D times P inverse. So this will give me a P times D squared times P inverse. Now, what if I want A to the power 3? Is the picture there? So what's A to the power 3? A to the power 3 is going to be P, and then I stop after that. That's A squared times the A. So this will give me P. P inverse and P are the identity, so they don't affect the product. D to the power 3 times P inverse. So if I want A to the 10 and I proceed the same, it's P times D to the power 10 times P inverse. So A to any power become, so finding A to any power, taking the power of A, will become simple. Why it will become simple? D to the 10, because D is diagonal, D to the 10 is very easy to compute. So if I don't have this factorization, I want to find A to the power 10, I have to take the matrix A, multiply it by itself 10 times. Just imagine you guys doing this. If it's diagonalizable, I just have to multiply 3 matrices by themselves. I don't have to multiply 10 times. It's just a matter of multiplying 3 matrices. So in the problems I have, A to the 10 is going to be the following. It's the product of those. P, I have it. It's 1, 2, 3, 7. D to the 10 is 2 to the power 10, 0, 0, 4 to the power 10. And P inverse is the inverse of that, which is 7, 1, minus 3, minus 2, because the determinant is equal to. So that's one first simple application of the diagonalization. It actually allows us to work with matrices in an easy way. So that's actually the good news. The bad news is not every matrix could be written this way. There is no way out. So the goal of this section is to study the following. Which matrices I can write like this, and which matrices I actually cannot write like that. In other words, which matrices are invertible and which ones are not invertible. Which matrices are diagonalizable and which ones are not diagonalizable. Which one I can break and which one I cannot do. So I will motivate the theorem and I will state it next time. So now today we're going to do a little bit, because we're going to state the theorem, but I would like to give you an idea what is really involved and what's the relationship between that and the eigenvalue problem. So we're going to basically motivate the theorem that I will state today, and next time I'll work with it. So suppose I'm going to work with 2 by 2 because it's a simple scenario. And let us say that I can actually diagonalize. I can do that. So the question is, what is those matrices? What's the D? What's the P? What's the relationship with A? So I'm going to multiply. So suppose this is possible. I will multiply by, I write multiply by P. So write multiply by P. I will have A times P equal to P times T. My goal is to show you what's this and what's that. So assume, since everything is a 2 by 2, this is 2 by 2, 2 by 2. So let me write P as V1, V2. Because it's a 2 by 2. D, I don't know what it is, but I'm looking, it's a diagonal. So I'm going to write it this way. That's my D. And I'm going to basically try to understand this condition. What is going on here? So I will multiply A times P. It means A times V1, V2. Now, there is one thing we saw at the beginning of the semester. If you guys remember that we talked about an equivalent definitions of the multiplication. And we said that if A times this, it's A times the first vector and A times the second vector. So I computed AP. Now I'm going to compute P times D, and I'm going to set them equal to each other. The idea is to try to understand the picture a tiny bit. So what's P times D? So P is the following matrix, V1, V2. And I want to multiply it by lambda 1, 0, that's my D, 0, lambda 2. All right. So this is a little bit not easy. So this is, so that's a vector and that's a vector. That's lambda 1, 0 and 0, lambda 2. All right, so I will use the same trick I used here. So this will be actually, I shouldn't have written P here. This is P times the vector lambda 1, 0. So that's the only hard part here. P times the vector 0, lambda 2. I'm using the same trick. Now what's P times lambda 1, 0? Let's do it on the side. P is V1, V2. When I multiply it by lambda 1, 0, what should I get? Can anybody figure that out? I know it's a little bit hard, but not. V1, V2 times lambda 1, 0 should give me what? It should give me, remember, the product of a matrix times a vector is the linear combination of the columns of A. So this will give me lambda 1, V1 plus 0, V2. So this one is right there because P is V1. So this would be lambda 1, V1. I will do the same trick here. So the same trick, it means 0, lambda 2. I will get 0, V1 plus lambda 2, V2. So this is lambda 2, V2. Now I'm going to put the whole picture together. AP, so we started, assume a matrix can be written like this. And I multiplied by P, right, multiply, means if this holds, I should have A times P equal P times D. So I try to compute A times P and P times D, and I got the following, that AV1 times AV2 is equal to lambda 1 V1, lambda 2 V2. So let me put the whole picture together because we are at the end of it. So let me put it together for you. So suppose A is a P times a D times P inverse. And assume that P is V1, V2. And D is the following diagonal matrix. A equal PD times inverse, it means AP equal PD, gave me the following. Gave me that. If this holds, it means AV1, AV2, that's this, should be equal to lambda 1 V1, lambda 2 V2. That's the setting I have. Now, how can two matrices be equal to each other? If AP equal to PD, it means this matrix has to be equal to that. It means the first column should be equal to the first column. It means AV1 has to be lambda 1 V1. And AV2 has to be lambda 2 V2. Okay. Now, V1 is not 0. Why V1 is not 0? Because V1 is the first column of the matrix P. And the matrix P, we're assuming it invertible, so we cannot have a column of zeros in it. V2 is not 0 for the same reason. The matrix P is invertible. V2 cannot be the 0 vector because it will not be invertible. So this tells me that a V1 equal lambda 1 V1, V1 is non-zero, and V2 non-zero. What does this mean? What's V1 and what's V2? So what's V1 and what's V2? Means V1 is an eigenvector. With absolutely. The eigenvector, they came out of nowhere. V1 is an eigenvector with corresponding eigenvalue lambda 1. V2, eigenvector with corresponding eigenvalue lambda 2. So the P is nothing more than the following matrix. The column is eigenvector, and this is eigenvectors of A. The D is the following matrix. V1 is eigenvector with eigenvalue lambda 1, and this one is 0 lambda 2. Lambda 1, the eigenvalue that corresponds to V1, lambda 2 is the eigenvalue that corresponds to V2. So a problem that seems absolutely not related to our initial eigenvector eigenvalue problem, but is just immediately showed up when we start working with it. So that's the relationship, one application of the eigenvalues, that it helps us basically to simplify the matrix. Now the question, 1 minute, and then we stop. Why not every matrix will be invertible for the following reason? This matrix P is invertible. So for the matrix A to be diagonalizable, those vector V1 and V2 has to be linearly independent. It means my original matrix A has to have 2 linearly independent eigenvectors. And that will be the condition under which diagonalization will be allowed. And this will be the content of the first theorem we're going to take over next time, is the condition under which we can diagonalize, which is going to be that we need in linearly independent eigenvectors, and how the diagonalization will occur. All right, I stop definitely at this moment. As you guys know, your exam grade is on Blackboard with the comments. If any student has any issue with the grading or the comment, please come to my Zoom office hours, and I will be glad to discuss them with you. All right, please go ahead and take the quiz. Good luck.